July 1974, mid-Pacific. The Hughes Glomar Explorer holds station 1,500 miles northwest of Hawaii, while engineers thread the first 60-foot pipe section into the moon pool. Below, more than 3 miles down, a shattered Soviet submarine sits on the seafloor, carrying nuclear warheads and codebooks. The crew is beginning a descent that will take 5 days, threading section after section of steel drill pipe through ocean that no cable or winch can reach. The target is precise. Lower a 179-foot steel claw onto a 132-foot wreck with a 10-foot margin of error. Miss that window, and the claw closes on sediment or empty water. There is no second attempt. The Soviet submarine K-129 had sunk 6 years earlier, settling onto the abyssal plain under 8,000 pounds per square inch of seawater pressure. Inside the corroding hull, cryptographic equipment, naval codebooks, and nuclear-tipped torpedoes. No nation had ever attempted a recovery at this depth. Standard salvage cables would snap under the load. Submersibles could photograph the wreck, but lacked the lifting power. The CIA concluded that if K-129 was going to come up, it would require a system borrowed from the oil industry. A drill pipe string strong enough to support millions of pounds through 3 miles of ocean. Each pipe section weighs 8 tons and spans 60 feet. Deck crews lift the sections with overhead cranes, aligning the threaded couplings within a fraction of a degree. Misalignment during threading creates stress concentrations, weak points that will propagate under load as the pipe string grows longer. The moon pool runs through the center of the ship, a concealed well 199 feet long. Soviet surveillance trawlers circle within visual range, so the massive doors remain closed except during deployment. Opening them takes 45 minutes and creates a 40-foot gap visible from aircraft. The pipe string must support the weight of the capture vehicle, the steel claw, plus the submarine itself. Total load? Approximately 4 million pounds. That is the weight of 2 fully loaded freight trains suspended through 3 miles of ocean. The drill pipe is operating at the edge of materials capability. Each joint must hold not only the tension of everything below it, but also resist compressive buckling as ocean currents push the string off vertical. Engineers calculated that even half a degree of misalignment during assembly could create bending moments that trigger catastrophic failure during the lift. Sonar operators track the descent in real time, sending acoustic pings down to the wreck and listening for the return. The positioning requirement is brutal, plus or minus 10 feet over a 132-foot target. Ocean currents at depth run up to 2 knots, drifting the pipe string horizontally even as it descends vertically. The claw must arrive within that 10-foot window. Missing it means the fingers close on sediment, or worse, on empty water. The hydraulic system cannot reopen the claw for a second try. There is one descent, one grab, one chance to get it right. The assembly and descent will take 5 days of continuous operation. Each new pipe section adds another 60 feet and another 8 tons of steel. The crew works in shifts, threading joints, lowering the string, checking alignment. There is no ability to abort mid-descent without losing the entire pipe string. If a joint fails during the descent, the claw and all the pipe below the break will plummet to the seafloor, and the mission ends. The operation is entirely committed. Once the first section enters the water, the only way out is down to the target and back up with the prize. At the bottom of the pipe string hangs the capture vehicle. A 179-foot steel framework fitted with 8 massive hydraulic fingers. Each finger is a 20-foot beam designed to cradle the submarine's cylindrical hull. The claw weighs hundreds of tons and must descend without tumbling or striking the seafloor too hard. Its hydraulic system is pre-charged but dormant. Once it reaches the bottom, the crew will have minutes to position it over the wreck, confirm alignment with sonar, and activate the hydraulics. After that, the fingers will close over 90 seconds and lock permanently. There is no mechanism to reopen them. After 5 days, the claw reaches 16,500 feet, and sonar confirms the submarine is directly below. The descent is complete. Now the real problem begins. threading a 179-foot steel needle onto a 132-foot target in absolute darkness, using only sonar pings that update every 30 seconds. Ocean currents continue to drift the claw across a 12-foot window. The crew has minutes to commit to the grab. If they wait too long, the claw drifts past the hull. If they activate too early, the fingers close on mud. The lift director watches the sonar display and prepares to make the call. The drill pipe is operating at the edge of material's capability. Each joint experiences compressive buckling risk if even half a degree off axis during assembly. A buckled joint will whip violently underwater, severing the pipe and sending the claw and submarine plummeting back to the seafloor with no recovery possible. The pipe sections are made of high-strength steel, but steel is not infinitely strong. At 4 million pounds of tension, the top joint is experiencing peak stress near 80,000 pounds per square inch, close to the material's yield limit. There is no margin for error, no reserve strength, no second pipe string waiting. The capture vehicle's hydraulic fingers are designed to close once. The system cannot generate enough pressure at depth to reopen the claw for a second attempt. Hydraulic fluid must overcome 8,000 pounds per square inch of ambient seawater pressure just to begin moving the actuators. The claw system is pre-charged to 10,000 psi to ensure immediate response. Once the crew releases pressure to the actuators, the fingers will descend over 90 seconds and lock. There is no hydraulic reservoir large enough to reverse the process. The closure is permanent. The grab must be perfect the first time. Standard salvage winches and cables cannot support 4 million pounds through 3 miles of ocean. Steel cable strong enough to handle the load would weigh more than the submarine itself, adding to the problem rather than solving it. Only a drill pipe architecture, borrowed from deep-sea oil rigs, has the necessary strength-to-weight ratio. The pipe is hollow, reducing its own weight, but still rigid enough to resist bending and buckling. This is not salvage. It is a mining operation disguised as salvage, using equipment that has never been tested at this depth or for this purpose. The engineers are improvising at the edge of known capability. Ocean currents at depth create lateral loads on the pipe string, inducing bending moments that add to the axial compression. The crew must maintain vertical alignment within 2 degrees. A 3-degree tilt over 16,000 feet translates to a horizontal offset of nearly 900 feet at the bottom, enough to miss the target entirely or create whip loads that snap the pipe. Real-time adjustments are impossible. The pipe string is too massive to steer. The crew can only position the ship precisely on the surface and hope the currents below do not exceed the design assumptions. The operation is a calculated gamble against forces they cannot see or control. Soviet surveillance trawlers circle within visual range, forcing the moon pool doors to remain closed except during pipe deployment. Opening the doors takes 45 minutes and creates a 40-foot gap visible from aircraft. Soviet reconnaissance planes fly over the site every 6 to 8 hours. Any visible evidence of the true mission, open doors, suspended load, extended pipe, will collapse the mining cover story. The crew operates on a strict schedule. Open doors, deploy 1 pipe section, close doors, wait for reconnaissance to pass. Every deployment window is a calculated risk. Every minute the doors are open is a minute the mission could be exposed. The submarine hull has corroded for 6 years under 8,000 pounds per square inch of seawater pressure. The steel is embrittled, weakened by oxidation and stress fractures. Original hull thickness was ½ an inch. Now it is closer to 3/10 of an inch in places. The material has lost ductility. It will behave like glass under tension, fracturing along grain boundaries rather than bending. If lifted faster than 3 feet per minute, dynamic stress will exceed the embrittled steel's fracture toughness, and the hull will tear along rusted seams. The wreck is not a solid object anymore. It is a collection of corroded fragments held together by hope and hydraulic pressure. The corroded hull cannot tolerate rapid acceleration. Lifting faster than 3 feet per minute would induce dynamic stress that exceeds the fracture toughness of the embrittled steel. 3 feet per minute over 16,500 feet means a lift time of 91 hours. Nearly 4 days of continuous, uninterrupted hoisting. The crew cannot stop mid-lift without risking thermal contraction in the hydraulic system, which could freeze the actuators and release the claw's grip. There is no pause button, no chance to rest or reassess. Once the lift begins, it must continue at exactly 3 feet per minute until the claw breaks the surface or the hull breaks apart. Either way, the outcome is final. There is no backup claw, no second pipe string, no reserve hydraulic system. Every component is operating at the edge of its design envelope. The engineers have built margin into the stress calculations, but those margins are measured in single-digit percentages, not factors of safety. One buckled pipe joint, one hydraulic seal failure, one miscalculation of hull strength, and the mission is over. The wreckage will fall back to the seafloor, deeper and more shattered than before, and the Soviets will eventually map the site and recover whatever the CIA leaves behind. The only safety net is precision. The only redundancy is competence. There are no second chances in this operation. After 5 days, the claw reaches the seafloor and sonar imaging confirms the submarine's position. But the wreck is worse than expected. The hull is partially buried in sediment and listing 15 degrees to port. The bow section is intact, but the aft has collapsed inward. Sonar reveals gaps where the pressure hull has ruptured. The target is not a clean, straight cylinder. It is a broken, tilted wreck embedded in mud. The crew must position the claw over the most intact section, the forward hull, where the codebooks and torpedoes are most likely to have survived. The margin of error just shrank. Ocean currents induce a 1.8-knot lateral drift at depth. The claw's position wanders across a 12-foot window, right at the edge of the 10-foot tolerance. Sonar updates every 30 seconds, but the claw moves continuously between pings. The crew is trying to position a football field-length steel frame onto a school bus-sized target using data that is always half a minute out of date. The operators can see where the claw was, not where it is. They must predict drift and commit to the grab based on extrapolation, not measurement. The current is not steady. It gusts and slackens. Timing is everything. The lift director must choose the moment to close the claw. Too early and the fingers crush sediment. Too late and the claw drifts past the hull with no chance to reposition. Video feeds from the claw are grainy and intermittent. The crew relies on sonar distance measurements that lag by 30 seconds. Real-time correction is impossible. The decision must be made now, before the data arrives, based on where the claw will be 90 seconds from now when the fingers finish closing. The director studies the sonar plot, watches the drift pattern, and calculates the intercept. The call is made. Activate hydraulics when sonar shows an 8-foot offset from centerline. The claw carries low-resolution cameras, but the video feeds are grainy and intermittent at this depth. Floodlights illuminate clouds of sediment stirred up by the descent, obscuring the hull. The operators can see vague outlines, shadows, occasional flashes of steel. They cannot see the hull clearly enough to judge alignment by eye. Sonar is the only reliable guide, and sonar cannot distinguish between sediment and steel until the claw is already in contact. The crew is operating almost blind. The grab will happen in near darkness, guided by acoustic echoes and faith in the calculations. There is no moment of visual confirmation before the fingers close. The hydraulic system is armed. Pressure is released to the claw's 8-finger actuators. The crew watches sonar and waits for confirmation that steel is gripping steel, not mud. 90 seconds until the fingers lock. The sonar display shows the claw drifting closer to the center line as the current carries it. 8 feet. 6 feet. 4 feet. The fingers begin to descend. Video feeds flicker and show movement. Sediment clouds erupt around the claw. The hull is somewhere in that cloud. The fingers are closing. The crew can do nothing now but watch and wait. The decision is made. The machine is in motion. The outcome is no longer in human hands. The sonar display shows the claw's fingers converging on the submarine hull. Distance closes to 0. Video feeds show sediment clearing slightly. Steel scrapes against steel. The hydraulic pressure stabilizes. The fingers have locked. The crew checks load sensors on the pipe string. The load has increased by millions of pounds. The claw is gripping something solid. Whether it is the hull or just a section of the hull, whether the structure will hold during the lift, those questions remain unanswered. The grab is complete. Now comes the hard part, bringing it up without tearing it apart. The lift director gives the order. Begin ascent, 3 feet per minute, 91 hours to the surface. Hydraulic fluid at 16,500 feet must overcome 8,000 pounds per square inch of ambient seawater pressure. At that depth, water is trying to force its way into every seal, every valve, every actuator. The claw's hydraulic system is pre-charged to 10,000 psi to ensure finger movement begins immediately when pressure is released. The actuators are massive, each one a steel cylinder 2 feet in diameter filled with incompressible oil. When pressure flows into the cylinder, a piston extends, pushing the finger downward. The fluid does not compress. The steel does not bend. The force is absolute. At 10,000 psi, each actuator generates roughly 300,000 pounds of closing force. Each of the 8 fingers is a 20-foot steel beam with a curved inner surface designed to cradle the submarine's cylindrical hull. Closure time is 90 seconds to avoid shock loading the brittle structure. If the fingers slam shut in 10 seconds, the impact force would shatter the corroded steel like glass. 90 seconds allows the fingers to descend slowly, making contact with the hull and gradually increasing pressure as they close. The geometry is calculated so that the fingers grip the hull at multiple points along its length, distributing the load across approximately 800 square feet of surface area. This keeps contact pressure below 500 psi, near the yield strength of the corroded steel, but not over it. The submarine's outer plating has thinned from ½ an inch to approximately 3/10 of an inch after 6 years of seawater corrosion. The steel has lost ductility. It will not bend. It will fracture along grain boundaries, snapping like brittle ceramic. The corrosion is not uniform. Some sections are weaker than others. Stress concentrations form wherever the claw's fingers make contact. The engineers know the hull is fragile, but they do not know exactly how fragile. The only way to find out is to begin the lift and monitor for cracks. If the hull starts to tear, there is no way to stop it. The lift must continue. Slowing down or stopping risks hydraulic system freeze up in near freezing water. Once the fingers lock, the load transfers through the claw's structural frame to the bottom joint of the pipe string. That joint experiences peak tensile stress of approximately 80,000 pounds per square inch, near the material limit for high-strength drill pipe. The pipe string now supports its own weight, roughly 2 million pounds, plus the claw and submarine, totaling 6 million pounds of tension at the top joint connected to the ship's lifting derrick. The load is not static. Ocean currents induce lateral vibrations. The pipe whips and flexes. Each joint must absorb bending moments in addition to pure tension. One misaligned joint, one microscopic crack, and the entire string fails catastrophically. The corroded hull cannot tolerate rapid acceleration. Lifting faster than 3 feet per minute would induce dynamic stress that exceeds the embrittled steel's fracture toughness, causing the hull to tear along rusted seams. Dynamic stress is the extra load created by acceleration. When the claw begins moving upward, the hull experiences not only the steady tension of its own weight, but also the additional force of being accelerated. At 3 feet per minute, acceleration is negligible. The hull feels only static tension. Any faster and the dynamic component rises sharply, pushing the steel past its breaking point. The lift rate is a physical necessity, not a precaution. 3 feet per minute is the maximum the hull can survive. A 16,500-foot lift at 3 feet per minute requires 91 hours of continuous operation. 4 days, no stops, no pauses. Stopping the lift risks thermal contraction in the hydraulic system. The deep ocean is near freezing. If hydraulic fluid cools and contracts, seals lose pressure, and the claw's grip weakens. Restarting after a stop could create a shock load that fractures the hull. The only safe path is continuous motion at constant speed. The crew will operate in shifts, monitoring load sensors, watching for cracks, adjusting the ship's position to keep the pipe string vertical. For 4 days, the mission is committed. There is no turning back, no reassessment, no margin for error. Video cameras on the claw transmit grainy images to the surface. Operators watch for cracks forming in the hull. Load sensors on the pipe string measure tension in real time. A sudden drop in load would indicate the hull has torn and a section has fallen away. Acoustic sensors listen for the sharp crack of steel fracturing. The crew has instruments, but the instruments cannot predict failure. They can only report it after it happens. The operators watch the screens and wait. Every hour that passes without a load drop is a small victory. Every frame of video showing the hull still intact is a reason to hope. But hope is not a plan. The hull will either hold or it will not. Brittle fracture occurs when stress exceeds the material's ability to deform. Ductile steel bends before it breaks. Brittle steel snaps without warning. Corrosion removes ductility by creating microscopic cracks and voids in the steel's grain structure. When tension is applied, those cracks propagate rapidly, unzipping the material like a zipper. Once a crack starts, it accelerates. There is no gradual failure, no creaking or groaning. The hull will be intact one moment and torn apart the next. The engineers cannot prevent brittle fracture. They can only minimize the stress and hope the steel has enough residual strength to survive the journey. The lift is not engineering. It is a controlled experiment in material failure at the edge of the possible. The lift begins at 3 feet per minute. The pipe string takes the load smoothly. The claw and submarine rise together through the darkness. After 12 hours, the load sensors remain stable. After 24 hours, the submarine has risen 4,300 feet and is still intact. The crew begins to believe the hull might hold. 36 hours in, the submarine has risen 6,500 feet and is halfway to the surface. Video feeds show the hull bending slightly but not fracturing. The steel is holding. The lift continues. The crew watches and waits. Every hour without failure is another mile closer to success. Video feeds show cracks forming along the hull's forward pressure bulkhead, propagating from corrosion pits near the claw's contact points. The cracks are thin, dark lines against the gray steel, growing longer with each frame. The load sensors have not dropped yet, but the hull is clearly weakening. The operators report the cracks to the lift director. The question is immediate. Continue at 3 feet per minute and risk the hull tearing apart, or slow further and extend the operation into a 5th day, increasing the chance of Soviet detection? There is no good answer. Every option carries catastrophic risk. The director makes the call. Maintain 3 feet per minute. Do not slow down. Accept the risk of hull failure. At 8,000 feet depth, the aft section of the submarine separates completely, tearing away from the claw and plummeting back to the seafloor. The load on the pipe string drops by 2.5 million pounds instantly. Load sensors spike negative as the tension vanishes. The pipe string whips upward, released from half its burden. The sudden load release sends a shockwave up the pipe, whipping the upper sections and risking joint separation. The crew must stabilize the lift immediately. The ship's derrick absorbs the shock. The pipe string holds. No joints have failed. But the aft section is gone, taking 4 nuclear warheads and the missile tubes with it. The forward section remains clamped in the claw. The crew stabilizes the lift. The pipe string has not failed. The derrick is holding. The forward section of the submarine is still clamped in the claw. Video feeds confirm the claw's grip has not loosened. The hydraulic system is intact. The load is now roughly 3 million pounds instead of 6 million. The pipe string is under less stress. but additional cracks are visible and spreading across the forward hull. The steel is still brittle. The lift must continue. Stopping now risks hydraulic freeze-up and complete loss of the remaining section. The director confirms. Resume ascent at 3 feet per minute. Get it to the surface before it falls apart completely. There is no other option. The lift continues. Every 100 feet gained is another victory. Every frame of video showing the hull still attached is a reason to keep going. The cracks continue to spread, but slowly. The hull is bending but not tearing further. The forward section holds together. The crew monitors load sensors and watches for the final catastrophic failure that never comes. At 4,000 feet depth, the hull is still intact. At 2,000 feet, still holding. At 1,000 feet, the cracks have stopped growing. The steel has stabilized. The worst is over. The forward section of K-129 is coming home. The claw will reach the surface with 1/3 of the submarine still clamped in its fingers. After 91 hours, the claw breaks the surface. The forward section of the submarine emerges into daylight for the first time in 6 years. Deck crews see corroded steel, bent plating, open hatches. The claw is winched upward into the moon pool. The forward 38 feet of K-129 hangs in the claw's grip, dripping seawater and sediment. The massive doors begin closing. 45 minutes to seal the moon pool before Soviet reconnaissance aircraft return. The crew works fast. The doors close. The submarine is hidden. The mission is complete. The Glomar Explorer is once again just a mining ship, holding station in the mid-Pacific. No one on the surface knows what just came up from the abyss. The forward 38 feet of the submarine is intact inside the moon pool. The section contains 2 nuclear-tipped torpedoes, codebooks, and cryptographic hardware. The midship and aft sections, including 4 additional warheads and the missile tubes, are gone, scattered across the seafloor at 8,000 feet. The CIA deems the mission a qualified success. The codebooks provide intelligence on Soviet submarine communication protocols. The torpedo warheads offer insights into nuclear miniaturization design. The intelligence haul is valuable, but it is not the entire submarine. 2/3 of the target was lost during the lift. The operation succeeded and failed at the same moment. 6 Soviet sailors' bodies are recovered from the forward section. The CIA decides to honor them. The bodies are prepared for burial at sea according to Soviet naval tradition. A ceremony is held on deck. The burials are filmed by the CIA for potential diplomatic release. The footage shows the bodies wrapped in weighted shrouds, a Soviet naval ensign draped over each, and the crew standing at attention as the remains are committed to the ocean. The film is classified and remains so for decades. The gesture is a quiet acknowledgement that the men who died aboard K-129 were sailors, not enemies. Professionals honoring professionals across the Cold War divide. The operation remains fully classified. The Hughes Glomar Explorer returns to port and is quietly decommissioned from CIA service. The cover story of deep-sea mining is maintained. Soviet intelligence suspects something but cannot prove it. The wreck site is too deep for Soviet salvage. The evidence is gone. For 35 years, the mission is a secret known only to a few hundred people. In 2010, Freedom of Information Act requests force partial disclosure. The CIA confirms the recovery attempt and releases some details. But the specifics of the codebook's contents, the full recovery manifests, and many operational details remain redacted even today. The mission is acknowledged, but not fully revealed. The Glomar Explorer's pipestring and capture vehicle design become the foundation for modern deep-ocean drilling and salvage. The operation proved that controlled lifts beyond 15,000 feet are feasible within narrow margins. Oil companies adopt the drill pipe architecture for deep-water drilling. Salvage firms study the claw design for future recovery missions. The engineering lessons are clear. At extreme depth, every system operates at the edge of material limits. Partial failure is not just possible, but likely. The mission succeeded because the design accepted that reality and prioritized the highest value targets in the forward hull. Success was defined as recovering something, not everything. The codebooks recovered from K-129 provide the U.S. Navy with insights into Soviet submarine communication protocols. The intelligence is not a war-winning breakthrough, but it is valuable. It confirms assumptions about Soviet encryption methods and reveals gaps in their operational security. The nuclear torpedo warheads offer data on Soviet miniaturization techniques, informing U.S. weapons development. The intelligence haul justifies the cost and risk of the operation, but barely. The mission was expensive, technically audacious, and only partially successful. Yet it provided information that could not have been obtained any other way. In the intelligence community, partial success is still success. The popular myth claims the CIA stole an entire Soviet submarine. The reality is more complicated. They recovered 1/3 of a disintegrating hull and had to watch the rest fall back into the abyss. The mission was not a clean victory. It was a brutal lesson in the limits of deep ocean engineering. The submarine could not be lifted intact. The hull was too corroded, the depth too extreme, the margin too thin. The operation succeeded only because the engineers accepted partial failure as inevitable and designed the mission around it. The Glomar Explorer did not steal a submarine. It salvaged what could be salvaged and let the rest go. The Hughes Glomar salvage demonstrated that Cold War intelligence collection had moved into a new domain, not space or air, but the deep ocean, where physics and engineering determined outcomes as much as strategy or secrecy. The mission proved that nations could operate at depths previously considered unreachable. The deep ocean was no longer a safe graveyard for secrets. Anything that sank could potentially be found and raised, given enough time, money, and engineering ingenuity. The operation changed the calculus of naval secrecy. Submarines could no longer assume that sinking in deep water meant permanent concealment. The abyss had become contested territory. The Glomar Explorer cost the CIA roughly $800 million in today's currency. The ship was built in secret, operated for a single mission, and then mothballed. The return on investment was 1/3 of a corroded submarine hull and a handful of intelligence insights. By any normal measure, the operation was inefficient and risky. But intelligence operations are not measured by return on investment. They are measured by whether the information obtained was worth the cost and could not have been obtained any other way. By that standard, Project Azorian was a success. It was expensive, audacious, and only partially effective, but it worked. And sometimes, in the deep ocean and in the Cold War, that is enough. The forward section of K-129 was disassembled and analyzed over several years. The torpedoes and warheads were studied and then destroyed. The cryptographic equipment was reverse engineered and the information archived. The hull structure itself was eventually cut apart and disposed of. No museum preserves the wreckage. No monument marks the site. The Glomar Explorer was sold to private industry and later converted into a deep-water drilling ship. It operated in the Gulf of Mexico and other oil fields before being scrapped in 2015. The capture vehicle and pipe string were dismantled. The physical artifacts are gone. Only the engineering lessons and the intelligence files remain. The mission established an unspoken rule in Cold War intelligence. The deep ocean is fair game, but success is measured in fractions, not totals. No nation has attempted a similar operation since. The cost is too high. The risk is too great. The return is too uncertain. But the precedent stands. If something valuable sinks, someone will try to raise it. The Glomar Explorer proved it can be done. The mission did not need to recover the entire submarine. It only needed to prove that recovery at that depth was possible. And it did. That proof changed naval strategy, intelligence doctrine, and deep water engineering. The mission's legacy is not what it recovered. It is what it demonstrated was within reach. Project Azorian was an operation at the edge of the possible. It required a ship that did not exist, a claw that had never been tested, and a pipe string operating at the limit of material science. It cost $800 million and recovered 1/3 of its target. The hull broke apart mid-lift. The mission was a partial success and a partial failure, both at the same moment. But it proved that the deep ocean was no longer beyond reach. It demonstrated that engineering, given enough resources and ingenuity, could operate at depths previously considered inaccessible. The mission's lesson is simple. At the edge of the possible, partial success is still success. And sometimes, proving it can be done is more valuable than doing it perfectly.